But today's talk, the title is From Field Programmable to Programmable. And I picked this title to try to draw a distinction between FPGA as logic devices in the past and my hopes and dreams for FPGA as computing devices in the future. So if you look at the term field programmable, it came from the time when we need a way to say there's a way to make an gate array ASIC without a mask. Field programmable means outside the fab. By programmable, I mean in the computing sense. So it is the kind of programmability we naturally associate with processors, right? With all the dynamism and flexibility that come with it, right? That is what I want programmable to mean when it comes to the future of FPGAs, and especially in the Crossroads FPGA. So the work I'm presenting today is the shared pursuit of many students that I listed here. Zapan and Joe, they're both graduating this summer. Shashank and Siddharth, they'll be carrying the torch forward. And one thing I also included Mary. So Mary is a former PhD student. I want to acknowledge her because her thesis laid the groundwork for a lot of things we're talking about today. And then let me also take this moment to thank Intel and VMware for very generously funding this work. And actually, beyond the funding we're receiving, I want to call especially to Scott Weber, Dasu Arvin, and Erika Nuvotati from Intel. And they've been working with us, interacting with us on this direction of work for more than 2 years. So thank you. To get going, to set the context, just a little bit of review from my last talk. The Crossroads Research Center was created to answer the question, what is the role of programmable logic in future data center servers? So when the Crossroads team asked ourselves that question, we pointed to the center of the server as the opportunity. Right? The envisioned Crossroads FPGA sits at the center of the server as a literal crossroads of data, supporting intelligent data switching between the server endpoints and providing inline processing of data that is on the move, traversing the switch. And the goal here is to manipulate data while they're traversing to minimize data movement and to reduce the amount of work, storage, or bandwidth that are needed at the downstream endpoint. And in this position, because of the volume and speed of data moving through, you can't afford to stall or to store the data. Right? If you want to do anything, you must keep up in real time. So in that sense, software is out of the question. And if you try to put an ASIC in this place, then we are limited to only the functionality that we can fit onto the chip all at once, and only to the functionalities that we knew about at design time. So an ASIC is also not a great answer. It's fast enough, but it's too rigid. So this is the sweet spot for FPGAs, precisely for its programmability and for the dynamism. So the goal of the Crossroads Center is to establish programmable logic in the form of a Crossroads FPGA as a central permanent fixture in the future server architecture. And as a fixture, right, a Crossroads FPGA will fill this role as a computing device. It is not embedded hardware, and it is definitely not a peripheral. And for that, field programmability is not good enough. So we have to think very hard about the programmability of Crossroads FPGA, how to use it, and how to design for it. And that's what today's talk is about. So my presentation will have 3 parts. I want to start by first convincing you of the need to start using FPGAs and designing for FPGAs differently from ASICs. FPGAs are programmable. We should use it correctly. Next, I want to highlight the work we're doing in Crossroads to now elevate programmability as a first-class capability of FPGAs. Then lastly, I want to give a preview of Pigasus 2.0. So last year, we open-sourced the RTL design of a 100 gigabit per second FPGA-accelerated network intrusion prevention system. We're calling the old design 1.0. In Pigasus 2.0, we have reconstructed the design specifically for FPGAs to gain additional improvements by doing things you would not do for an ASIC design. So indeed, to design for FPGA differently than from ASIC. So that's the outline for today's talk. And yeah, for this talk, I have not quite decided if it is better if you, the audience, you know a lot about FPGAs the way it was, or for you to know nothing at all. So in any case, please stop me if with questions, anything's not clear. So let's get moving. All right. So to start, let's ask this question: what is different when designing for ASIC versus designing for FPGA? Right. This, it's not a trick question. It shouldn't be a trick question. Very simply, an ASIC design has to be fixed at design time. FPGA designs don't have to be. But unfortunately, to date, most FPGA designers are trained to think like ASIC designers. And so in that way, when we're solving a design problem, whether you're an ASIC designer or FPGA designer, we're there to work out two basic things. Number one, what to include in the design. And number two, how much resources spent on each part as optimization. So if you look at the cartoon on the left here, right, I'm showing you a very simple design with 3 modules, 1, 2, 3. And as an ASIC designer or FPGA designer who think like an ASIC designers, I would have done a good job if I correctly allocated the available logic area to the 3 modules such that I get the best overall performance, right? This is optimal if I cannot do any better for the same area given to me. Well, it would be optimal unless we also start looking in the time dimension. So suppose modules 1, 2, and 3 are only ever used one at a time. So on the right, I'm showing logic resources, now not as an area, but as an area time volume. There's a third dimension to it now. Because the FPGA fabric is programmable, right? The correct way to do resource accounting is in terms of area time volume. And under this interpretation, right, you can clearly see a static ASIC style design is not the best you can do to use up the resources, the area time volume resources of an FPGA. Right? Because FPGA fabric is programmable, what a region of logic fabric is used for can change over time. If modules 1, 2, and 3 are only used one at a time, they should be mapped to reuse the same region by dynamic partial reconfiguration. And for those of you who are not familiar with partial reconfiguration, it is a technology where a portion of the FPGA fabric can be reconfigured while the rest of the fabric continues undisrupted. And you may be surprised, right? This technology has been available for a long time. It's just that you never ask about it if you design for FPGA like an ASIC. So using partial reconfiguration or PR, right? to reuse a region. Now, if you see on the top right, I can get the same performance as the left, now using less area. If you say, then what's the extra area for? Well, this will make sense, right? If it were also in our mindset that FPGA fabric that I don't use can be used by someone else, right? This can be and should be someone else, just like in a multitasking CPU. A computing FPGA should and can also be shared by multiple tenants. And alternatively, but this showing you someone else. So alternatively, right, if we look on the bottom right, I can also now using partial reconfiguration, I can also make use of different implementations, bigger, faster implementations of the same functionality of modules 1, 2, 3. In this case, I'm using up all the fabric, but now I get more performance. And what's even better is that, right, there's nothing that says I can have both variants of module 1, 2, 3. The small one and the big one, I can have this around. And I can use one set at daytime. I can use another at nighttime to achieve different trade-offs. And maybe I can even mix them at different times for different trade-offs, right? So this is what in a cartoon way, this is what I mean by using and programming FPGAs dynamically. And to get to design like this, right, it requires us to start to develop a different mindset from ASIC designers. So, it's one thing to wax philosophical with a cartoon, right? What if I told you, right, once we know what to look for, we started to see missed opportunities everywhere. So take, for example, the Pigasus network intrusion prevention system, right? This design can check 30,000 stored rules in real time at 100 gigabit per second using just one FPGA and one CPU. It's a beautiful design. And if you were here for last week's talk, you know something about Pigasus, but let me review a little so we get to the same place for what I want to focus on today. So to understand what Pigasus does, right, first you need to realize it is not possible to actually check 100 gigabit per second of traffic against 30,000 rules, at least not literally, right? These rules include very expensive regular expressions as conditions that to check for. So there has to be a shortcut in a good design. And what the slide is showing you is that as network traffic enters from the left, after TCP reassembly, the first thing Pigasus does is to do the simplest, cheapest checks first. So the multi-stream fast pattern matcher. So in Snore, this means looking for just one exact string for each rule, right? These is what's called a fast pattern. And empirically, what you expect to see is that about 85% of the traffic don't match any of the fast patterns, therefore not any of the rules. And then we can conclude immediately they're safe, nothing more needs to be done. For the remaining 15%, Pigasus makes another pass, doing the next set of more involved checks. Still not the regular expressions. Those are too expensive. But what this stage, right, this stage is what we call the non-fast pattern matcher. And this can clear about 10% more of the traffic as safe. So at the end, less than 5% of the traffic remains suspicious and has to be checked completely. And that we forward to the CPU to do. So, that's how the Pigasus work overall. And today, what I want to focus specifically on this piece of the design. the non-fast pattern matcher, the second filter. So this non-fast pattern matcher, or NFPM, if we have to abbreviate, it sits downstream from the fast pattern matcher. It performs more detailed checks to decide if a suspected packet is actually safe, a false positive from the fast pattern checking. So unlike the fast pattern checks, which is very simple, very uniform across packets and rules, the non-fast pattern checks have many variations depending on the packet and rules involved. It is not a simple or cheap module, but fortunately, it doesn't have to run at the full 100 gigabits per second. And empirically, we have found designing for something like 20 gigabits per second is almost always good enough. But that assumes typical traffic. If there's a denial service attack, many more packets will be directed to the non-fast pattern matcher. And even without an attack, an unlucky burst of innocent packet that happens to contain the fast pattern strings can also overwhelm this non-fast pattern matcher if we design it only to handle the common case traffic profile. And you end up in a catch-22, right? You don't want to pay for a more expensive non-fast pattern matcher when the extra performance may never be needed. And so in Pigasus 1.0, this is last year's design, what we did is to have an overflow path to where we can dump excess work to the CPU in the rare cases when the input load goes above typical, right? And this works, but it only works for very short temporary excursions, right? Because the CPU is so much slower at checking. But if you design like ASICs, this is the best you can do. Now, if you put on your FPGA thinking hat, then there's a lot more, right? With an FPGA, I don't have to live with a static, predetermined design compromise. So for this slide, right, you have to imagine a multi-tenant shared FPGA. So that means the regions of fabric not used by Pigasus, I'm assuming someone else is paying to use it. So for the baseline design of Pigasus, I am motivated to use as little logic fabric as I need for the common case performance. Now, if Pigasus ever come under attack or just get unlucky, the baseline matcher will be overrun. We can stay afloat for a small window of time by doing this overflowing to the CPU. But when this is happening, right, when this exceptional case is actually happening, I am much more willing to pay more to use more of the fabric. So on a dynamic partial reconfigure FPGA, then what I should do is now on demand, when I need to allocate more fabric, I can use partial reconfiguration to load up a second helper non-fast pattern matcher to handle the increased load. Maybe I will even splurge. I can load up a bigger helper just in case. And if it turns out to be a full-on denial service, maybe what is needed is actually to allocate more fabric, not only on this FPGA, but on many more FPGAs, and we get to them over the network. So, sorry about that. I'm hopping around a little bit. But I'm not designing for an ASIC. I don't have to design for the worst case that may or may not ever happen. And instead, right, on an FPGA design, I should respond dynamically to dynamically arising conditions. This is programmability, and this is the dynamism I'm promoting. What's interesting is, right, when you start thinking like this, right, when you take out this new mindset, you see the world very differently, right? For one thing, now you get to ask this very interesting question. How much is PR, partial reconfiguration speed, worth? If I make partial reconfiguration faster, how much is it worth? And we can do this quantitatively, even in dollars, right? So what we said on the last slide was that, right, we want to start with a cheap but good enough baseline non-fast pattern matcher. When we detect the baseline falling behind, we allocate on demand a second helper matcher by partial reconfiguration. Right? This technique of allocate on demand, right, it really only works if the helper comes online before the buffers and the baseline systems overrun and we start dropping packets. So the speed, the partial reconfiguration speed matters. And without going to the nitty-gritty, right, you can imagine we can build a simple analytical model that looks at the various buffering capacity, the processing rate, and the latency of partial reconfiguration as parameters. And for different models of bounded input load excursions, for example, we can assume a step increase where the load suddenly jumps and stay there, right? For a excursion model, for the input excursion, if you give me a set of design parameter values for the analytical model, I can tell you if this allocate on demand solution can avoid packet loss, right? That what that means is, right, there is enough overcapacity built into the baseline system to not drop any packet until partial reconfiguration can get the helper running, right? There's this race condition. Drop packets, PR, the helper starts to run. And that's one question, right? There's a more interesting problem if you invert the question. So again, for a input excursion model, what I could also do is go ahead and solve. I can solve for all parameter sets that do not drop packets. What are the valid designs? And if you think about the solution space to this inverted problem, right? You see that the extra cost, how much I need to over-design the baseline, has to be directly related to how long partial reconfiguration takes. If partial reconfiguration is fast, I need less over-design. If partial reconfiguration is slow, I need more. And so now I actually have a quantitative way to say how much is PR speed worth in this design in terms of logic area that I don't have to over-provision in a common case. And this, gets up to a very fascinating new direction. So that's the first part of the talk. And at this point, right, I hope I convince you, I hope I convince you that there is a real need and opportunity for us to embrace the programmability of FPGAs and how we design for FPGAs and how we should use FPGAs in the future. And, for this talk, I also have to say, right, if you're not convinced, then I need to ask you to temporarily suspend your disbelief for the next 30 minutes, right? Well, the rest of the talk will make no sense at all, okay? But if you're ready, then let's take a look at the second part where we talk about what we plan to do to capture the programmability and dynamism of Crossroads FPGAs. Okay, so in my mind, right, this RV5, this research vector, The research efforts are laid out in 3 layers. So at the first level, we need to give users and designers new ways to think about FPGA design that are different from how we use ASIC. We need to work out what we want to do with programmability and be able to quantify its value added, right? We saw the allocate on demand example earlier. It's one example. There are many other techniques to be worked out, right? I mentioned multi-tenant sharing. That is definitely one of them. And after we have collected these desirable new design styles and application usages, then we need to get into enabling those ideas by developing the programming and runtime environment to actually support them. And finally, right, the decisions from the above then can start to drive the answers to how the FPGA fabric architecture, the partial reconfiguration mechanism, how should they be the hardware? How should the hardware be evolved to support the future, how we intend to use and to design for FPGAs in the future. So like the first bullet, right, we touch on the first bullet, that's what I try to do in the first part of the talk. And so for this middle part, let's talk about the second and the third bullet. And we'll start with the hardware first, actually. The reason we begin with hardware is that there are some hardware design decisions that are so basic to our thinking, we are committed to them as axioms. They're not challengeable. So first, right, Crossroads FPGA, the Crossroads Center, is not going to get into reinventing a better logic fabric. We're happy with the fabric architecture of Stratix 10 or Agilex or Xilinx. We want to use 3D integration to stack a mostly vanilla logic fabric on top of a base die that will separately contain the specialized Crossroads mechanism. And what you see in the picture on the right is that, right, with a mostly vanilla fabric, right, a feature that we're asking for on the bottom die is the use of network on chip, right? We want to use network on chip for long haul data transfer in this computing application. And if we have going with the 3D implementation, then the network on chip will be pushed onto the base die, and the top die will only be disrupted with on-ramp and off-ramp for the network. So first, right, using network on chip for long-haul data transport. Second, I think to move forward in this direction, we must have relocatable PR bit streams. Bit stream that I can use in different places on FPGA. And to get it, I will settle for having PR management quantized to only on whole sector or whole tile boundaries, right? I don't actually need the freedom to control partial reconfiguration down to individual columns or partial columns. I'm allowed to do that today, right? I'm willing to give that up, going for the sector boundaries, and in return, at that sector granularity, the same PR bit stream should work on any sector tile of the same type. And so we need to be, going forward, be much more deliberate about actually keeping the sector tiles uniform as a design requirement. And then finally, last thing, relating back to the NOC, right? In the Crossroads FPGA, I'm going to impose that Crossroads PR, partial reconfiguration modules, can only interact with each other by going through the network on chip and using latency-insensitive streaming or message passing. I'm not putting any limits on how many sectors one module takes up or what you want to do inside a module. Right? What I care about is what happens when you go outside a module and when you interact with outside the module. And later we'll come back to see how these three basic strategies form the basis of a virtualized design and execution environment. So also at the hardware level, right, there's always, if you're working in partial reconfiguration, right, there's the elephant in the room question. Right? It has to do with the speed and modality of partial reconfiguration. And my comment on that is, I agree, right? The status quo of today's partial reconfiguration support is not very good. But we should all keep in mind, right? The status quo is only a reflection of how we are using partial reconfiguration today. And for how we use it, the value we place on it. And given that most of us still design FPGAs like an ASIC, you can imagine, right? There's a lot more room left for improvement. So, let's go back. Let's go back to the allocate on demand technique from earlier. And truth be told, right, at today's partial reconfiguration speed, at best milliseconds, it is a non-starter for what I need in Pigasus, right? But if you think back, right, what we also saw is that for the technique, right, we could place a quantitative value on what happens if partial reconfiguration got faster. And with that, the question becomes, is there enough value to justify making partial reconfiguration faster? Say, for example, 10 times faster. Now, if you're thinking there's no way to make partial reconfiguration suddenly 10 times faster, you're not attacking the right problem. I don't want to make today's partial reconfiguration mechanism 10 times faster. Right? If you think back to the allocate on demand example, right, where what we need is a different kind of partial reconfiguration than what we are set up to do today. The value that's generated is in having just one very high priority bit string that I know I may need to activate as quickly as possible. It's a very specific usage. And given enough value, right, could there be a new partial reconfiguration mechanism where I get to pre-stage that one hot bit string so that it can be ready much faster than what we're doing today? And if you think also that in that particular example, right, I have a helper running. If all I want to do is to make an exact copy of the baseline non-fast pattern matcher that's already on the fabric, then, right, is there not a way to clone the sector much faster than what quarters will allow us to do today? And these are new, right, new mechanisms justified by new usages. And, keep in mind also that, right, the incremental cost may not have to be very high. So in the Crossroads FPGA context, right, we're already putting a narrow-down chip. We're going to put all kinds of memory and other things on the bottom die, right? They're already going to be there for other reasons. They can also be used to support these new faster PR modes. And also, whatever we do to enable, to help this allocate on demand use mode, it could also generate value added for other uses. And all these have to go together into the cost benefit analysis of what PR hardware improvements are required, are justified. And so these are the kind of questions that my group has been working on, starting today with the example of allocate on demand in Pigasus. But having these real examples, these concrete examples, is very helpful, right? You can't work out how to improve partial reconfiguration, what is actually needed in the absence of an application of value. So on this last bullet, right, I'll admit, right, I'm just very casually listing a series of related connected problems that I think ultimately we have to work through in the same way, driven by application, right? By knowing how we ultimately intend to use and to design for FPGA. And I am going to very blatantly gloss over this last bullet. Don't fault me. I switch gear. And now let's move up a level. And now we can ask, right, at the next level, what should a Crossroads FPGA application developer see when creating an application? I don't want any designer, or if you like an application, right, to see the whole Crossroads FPGA, not in its entirety and not in full detail, right? We need to have an API, an application programming interface, so that we can show the designer just what they need to see, but leave enough degrees of freedom for the compiler and runtime systems to control things. Remember, right, Crossroads FPGA is not an FPGA for arbitrary RTL netlists, right? It's a computing FPGA, and the applications on Crossroads, they're computing applications, and they should lend themselves better to modular construction and abstract interfaces. And as such, right, we are in a position to dictate what a module can and cannot do, at least at its input and output boundary. So what I'm showing in this slide is at the highest level, right, I'm going to impose that any Crossroads application be composed of PR modules. It could be one module, could be many modules cooperating together. But in any case, right, the partial reconfiguration is the fundamental mode of operation on Crossroads, right? Partial reconfiguration is the only way to start an application on the Crossroads FPGA. No application gets to own the FPGA, the entire FPGA. No application gets to own the FPGA forever, right? Partial reconfiguration is the fundamental mode of operation. Now, in the PR module that make up an application, some of them will be developed specially for the application, but we also want a lot of them to be provided by the system as library IPs to support common operations and to hide platform details. Right? This is analogous to having standard library functions and system calls when you write C programs. And we said earlier already, like, partial reconfiguration will only take place on whole sectors, but one module can take up any number of adjoining sectors. And within the sectors of one PR module, right, inside, it can still be a very traditional synchronous RTL environment. Right? It is when you go outside, then these PR modules are only allowed to interact with each other through the network on chip and by latency-sensitive interaction. So if, again, you're using a cartoon, on the bottom, I'm showing a two-module design where imagine module A is an application kernel. It takes up three sectors, three squares, three sectors of some footprint. Right? That is the scope of what the designer of module A needs to know about the fabric. those 3 squares. And also, right, although the overall application uses DRAM, the designer of module A doesn't have to understand DRAM directly. So what's shown in this picture is that, right, there's a library module B that is an intermediate. It's providing access methods supporting a high-level data structure object, maybe a graph, maybe a sparse matrix. And the designer of module A doesn't have to know how data is represented in memory or where things are stored exactly. Right? It's supported to be with an abstraction. And the goal of having an API like this, right, is to limit global knowledge and to limit the physical binding decision that has to be visible at design time. Right? This is very important because we want to give Crossroads compiler and the runtime system the ability to make those decisions for the designers later. In terms of concrete technology, we have been working on a framework that we refer to as service-oriented modular design. Right? This was work originally done for a compile time design composition, but we very quickly realized its usefulness and applicability as a dynamic abstraction as well. So if you think about it, right, if you've done Verilog design, a Verilog module IP is almost impossible to use as a black box. Right? Why is that? Right? When I wire up to the ports of a Verilog module, that's easy. I know the names of the ports. I wire up to it. Right? So for a module written by someone else, I can look at the declaration. I can wire it up. But having done that, I have very little expectation that it is going to just work. Right? Nothing happens unless I actually understood exactly right the timing and sequencing of the interface signals on the ports. And even after I figured that out, right, so I can actually get the module to work in the functionality sense, it gives me the right answer, right? It still may not suit me in the performance and cost trade-off. Right? So one way or another, I always end up having to do some work inside a Verilog module IP. So the goal of this service-oriented design is to impose an abstracted interaction between modules to make plug and play possible. And for the full detail, I'm going to invite you to watch. You see on top, there's a YouTube link. All the talks in the seminar series will be posted to YouTube. And so there was earlier a seminar given by Joe Melber. So if you're interested for the full detail on this slide, I only invite you to watch a YouTube. But for today, right, let's go by example. So imagine you're developing a graph processing accelerator, like breadth first search. Right? Normally, if you're doing the FPGA accelerator, the same designer, the same person is dealing with the algorithm, the graph representation, all the way down to the quirkiness of DRAM. And so that one person had to be a jack of all trades. Let's not do that, right? That encapsulates the graph representation as a service, so the algorithmic kernel gets to operate at the graph level, like asking for the neighbor of a node. And it is the graph service job to understand what that means in terms of actual graph representation. And in a hierarchical construction, the graph service itself is supported by a memory service, so the graph service doesn't understand the difference between DRAM and HBM, or if there's cache introduced. Right? This separation of concerns make designing hardware simpler and more portable. It can also lead to higher performance if services are created by specialists and provided as reusable libraries. And from that, we can add a dynamic dimension to the picture by combining services with partial reconfiguration. And on this slide, I'm showing a proof of concept study where we're using service-oriented abstraction and partial reconfiguration to dynamically compose new designs to change functionality and performance. And starting with the best first design we talked about, while running, using partial reconfiguration, we can switch out the algorithmic module by a different graph algorithm like single source shortest path. And the new computation can start running with the same graph and memory service module. And similarly, we can switch between different sparse and dense graph representation by changing out the graph service modules without affecting the algorithm kernels. And then we can even do things at the memory service module, like introducing caches to change the performance to cater to the data set. And this is something that's working today. It is still a limited prototype, but it works. And I think starting from this, we can start to figure out how to make it better. And here, very quickly, is another design that we're using to virtualize the target platform from the designer. Right? We can take a streaming design like Pigasus 2.0 and assign the nodes to the same FPGA or to this aggregator across multiple FPGAs. And in the design, right, logically, the streaming nodes only interact point-to-point by FIFO-like channels. The sender and receiver have no understanding of if they're on the same or different FPGA, or how the communication channels are actually constructed. Right? This you will be able to do in Pigasus 2.0. So if you don't think I'm crazy by now, then let me put it all out there, right? So here are my high-level goals for programmability and dynamism on Crossroads FPGAs. Putting the ideas we talked about together, I want designers to be able to create TR modules that are location independent. I should be able to load a module anywhere where I have free tiles of the right footprint. And thinking dynamically, I should be able to also at runtime move a module to another set of free tiles of the right footprint. And keeping in mind, right, it takes more than relocatable bit streams to have relocatable modules. We have to virtualize how modules interact externally. Right, from there, right, by requiring the use of latency-insensitive channels in the design abstraction and mapping them to a network on chip, right, the goal is to be able to locate and relocate interacting PR modules independently, either at compile time or runtime, right? The decoupled timing relationship is important for runtime management. If I ever need to disrupt execution of A or B at runtime, either for time sharing or to do relocation. And to go one step further, right, at some point, I may decide to stop module B, like in this example, mid-execution, to replace it by a higher performing variant. Like this is the example, this is what we wanted to do in Pigasus for the non-fast pattern matcher, right? Module A, the rest of the design doesn't need to know. And it is the interface abstraction and the latency insensitivity that makes this possible. I think I need to go a little faster. So with everything we've set up, right, multi-tenancy falls out quite naturally. And whatever A and B are not using, they don't need to know. And so the runtime system can let multiple applications use the fabric concurrently in a safe and transparent way. Right? There is a quality of service question on sharing the network on chip. Actually, right, this quality of service question, it will arise even with just one application because we can place them differently. And so as part of that design API, we do need to give the designer a way to express the communication performance constraints, the communication requirements, and the tools need to be able to factor those requirements in the scheduling of the fabric and the network on chip. And if we come this far, right, why not use abstraction to allow design to go across multiple FPGAs? And if you notice, right, the example on this slide and all the ones before, right, they're all based off the same abstract design at the API level, right? Just with different physical binding that's decided separately, either at compile time or runtime. And this is the dynamism, the programmability that I want the Crossroads FPGA to get to at the end of the project. So I'm quite a bit behind. I do have one more topic to cover. We might be just a few minutes late when I finish. So I'm going to keep going. This will be recorded. If you need to leave at 3, please do so. You can catch me on YouTube later, but I will finish it. Sorry about that. I don't know why I'm behind. I thought I was doing well. All right, let's keep moving. So the last topic, that Pigasus 2.0. So when I said Pigasus 1.0, I mean the RTL design we open sourced last year, right? That design, it was still designed with a traditional ASIC style mindset. Pigasus 1.0 will make a very good design, whether you compiled it for an FPGA or for ASICs. But because we limited ourselves to a fixed ASIC style design thinking, based on what you saw today, we should understand that Pigasus 1.0 is not the best we could do on FPGA. So in what we call 2.0, we really went after reconstructing Pigasus to exploit FPGA's programmability. So right off the bat, right, I don't want you to think of Pigasus 2.0 as an RTL design. And it is not even a one-off design in the traditional sense. Right? Pigasus 2.0 is a design template that gives you a space of designs to choose from. I don't want to decide the design instance for you. Right? You, as a user of Pigasus 2.0, you should see a streaming network of nodes. Each stage is abstracted as a streaming processing service module, service node. And they are interacting using these point-to-point latency-sensitive logical channels. Each node itself is parameterized so you yourself can node by node individually set their cost-performance trade-off point. And the communication channels, they're logical, so their physical interface and the resulting performance, it will scale automatically with the parameter you set for the node. So everything is plug and play. So the goal, right, the ultimate goal for Pigasus 2.0 is this one deployment, one design. For every deployment scenario, depending on the size of the FPGA available to you and what you know about the operating condition, you get to choose a design optimized for that particular deployment, right? If you can afford to spend 2 FPGAs, you get to do that too, right? With a programmable FPGA, right? Why should 2 different deployments have to be stuck with using the same design? And so the punchline says, right? FPGA offers something more than ASIC, right? We need to use it correctly. So one deployment, one design. And going to the second point, right? So first is about compile time choices. Then, as we saw with this allocate on demand technique, we also want to allow a deployment to change the design trade-off even at runtime using partial reconfiguration. And especially in a multi-tenant scenario, at any point in time, I should only have to pay for as much resource as I need to hit the performance I need. Right? My willingness to pay for resources goes up and down with my traffic-dependent performance needs. And then finally, right, beyond what Pigasus 2.0 lets you choose from, because Pigasus 2.0 follows a plug-and-play streaming service paradigm, it is an open-ended design space. It will be very easy for you to modify, to substitute, or insert your custom nodes. Right? You can do this either if you want to make a better Pigasus, or you want to make a completely unrelated application, just reusing the IPs you find in Pigasus as infrastructure. On this last point, right, this is something that we actually started to do, but we are taking Pigasus 2.0 apart to use it as infrastructure for building other in-network compute applications. Right, if you look at the Pigasus pipeline, if I take out the snore rule matchers, right, what's left is just an infrastructure for streaming analytics. For example, right, if we feed the same data path with Twitter text streams, we can use the same Pigasus fast pattern matcher to extract keywords from the text stream. And then using those keywords, we can build feature vectors from those Twitter messages. Then we can introduce apps downstream a streaming inference engine. Then now we can do sentiment analysis at line rate in real time. And so this is one example of what we're doing. I'm sure you can think of many things to do with this as well. And we are going to release Pigasus 2.0 this summer, right? It will have everything I said except this dynamic allocate on demand feature. This will not be in 2.0, right? This is still ongoing work. So Shashank, a student, right, he has a proof of concept demo working in the lab, but there's a lot more that needs to be done before this is practical for real use. And what Shashank's being able to do is already very impressive, right? But a lot more needs to happen. So maybe you can look for this next year. Okay, only a couple minutes late, but to close it properly, right, I really have just one message today. So as users and designers of FPGA, right, let us break free from the old ASIC mindset and learn to use FPGA's programmability. And so here I list 3 points. On this first point of dynamism, right, we heard today that by reprogramming FPGAs, we not only can get more flexibility and functionality out of FPGAs, but programmability actually also gives a way to squeeze more performance and efficiency from FPGAs. Then on the second point of sharing, especially in a data center server, right, we should think of an FPGA as a programmable computing device and not fixed function embedded hardware. Right? It is a resource that we can share by programming it and using only as much as we need when we need it. What we don't use, we let someone else use it and let them pay for it. And lastly, right, to go from this embedded hardware model FPGA to a programmable, shareable compute resource, right? Ultimately, we will have to incorporate FPGA under OS management. And this means developing a proper architecture of interfaces, virtualization, and isolation that the OS can understand and manage for us. So these are what we want to do. There's a lot to do, right? But it's a very interesting time. Right? This transformation of FPGA from logic to computing device is actually well underway. And I think what we want to do, right, what we get to do is to help it go the entire way. Right? This makes a very exciting time. I'm sorry for running over, but that's all I have. I want to thank you for attending and staying around.